In order to draw molecules, you just have to follow some simple rules. In order to get good at drawing molecules, you'll have to do several examples on your own. I'm going to go through 3 examples and show you the different ways that molecules can be drawn, including double and triple bonds, and those that bust the octet rule. Here's the first rule that you need to know when you're drawing molecules. Put the least electronegative atom in the center. Between carbon and chlorine, carbon is the furthest left on the periodic table and the furthest down, so it is the least electronegative. So I put it in the middle. The second step is to place the remaining atoms around the central atom. Notice I put all 4 chlorines around the carbon, and I put them as mirror objects of each other. The third step is to draw lines between them to represent a covalent bond. Remember that each dash represents 2 electrons being shared between those 2 atoms. The fourth step is to count the total number of valence electrons. You'll get this from the periodic table. Carbon is in group 14 and therefore donates 4 valence electrons to the molecule. Chlorine is in group 17, so it'll donate 7. But remember, there's 4 chlorines in this molecule. So if we count up the 4 from one carbon and the 7 from each of the 4 chlorines, you get 32 valence electrons in this molecule. We're going to subtract 8 electrons from the total because of the bonding. Remember that each one represents sharing of 2 electrons. Now we're left with 24 electrons. These will be used for lone pairs and non-bonding electrons. In the sixth step, we place the remaining electrons around the central atom until it has a total of 8. This carbon here already has 8 electrons around it, so we don't need to do it in this case. In the seventh step, we place the remaining electrons around the terminal atoms until each has a total of 8. If you count up the total dots around each of the chlorines, each one has 6, and there are 4 chlorines, giving us a total of 24. That is the exact amount of valence electrons we had left after the bonding. So you check and see if everybody's octet is full, and if it is, you are done drawing the molecule. We are done with this one because everyone has 8 electrons around them. Here's an example of one that has multiple bonds. Carbon dioxide, or CO2. Notice I've put the carbon in the middle, and I've surrounded it by the 2 more electronegative atoms on the sides, in mirror images of each other. If I count up the total valence electrons, carbon has 4, and oxygen has 6, and there's 2 oxygens, giving us a total of 16 valence electrons. We're going to go ahead and subtract 4 because there's 2 bonds, each sharing 2 electrons. That gets us down to 12 valence electrons. Remember, the next step is to put the remaining electrons around the carbon until its octet's full. That gets rid of another 4, and now carbon has 8 around it, and its octet is full. The remaining 8 electrons would go around the oxygens on the outside. Notice I put them equally dispersed between the 2 oxygens. If you notice now, the oxygen only has 6 electrons around it, not enough to fill its octet rule. So what will happen is the 2 electrons around carbon, which are only used for lone pairs, will be stolen by the oxygen being the more electronegative atom, and they will be shared with carbon and oxygen instead of it being only with carbon, and it will form a double bond. Notice I erased the lone pair when I created the double bond. I'm going to do the same thing for the other oxygen. So I will take this lone pair from carbon, and it will also become a double bond. Now let's count up their valence electrons. Oxygen has 4 electrons found in 2 lone pairs, and 4 electrons being shared with carbon in the bond. That gives it a total of 8. Carbon has all 8 of its electrons being shared with the oxygens, so it also has a total of 8. Everyone's octet is full, so we are done drawing the molecule. Here's another situation that can pop up. This is xenon tetrafluoride. Xenon is one of the exceptions that can have an expanded octet, or have more than 8 electrons in its orbitals. So I've drawn xenon in the middle, and the fluorines around it as mirror objects. Xenon is the least electronegative. If I count up the valence electrons, xenon is a noble gas, so it will donate 8, and fluorine is a halogen, so each fluorine will donate 7. Since there's 4 of them, there will be 28 donated. That gives us a total of 36 electrons. If we subtract 8 from the bonds, we're down to 28. So we'll look and we see the first place we put them is around xenon until it has 8 electrons around it, which it already does, so we're going to skip that step. Then I'm going to put all the remaining electrons, or all 28, around the fluorines. But if you count how many we could put around the fluorines until their octets were full, we could only fit 24 electrons around the fluorine. So since we could only fit 24 electrons around the fluorines, we have 4 left over. If this is the case where everybody's octet is full, but we still have remaining electrons to put in the molecule, we're going to place them around the central atom. Notice that xenon now has a total of 12 electrons around it, which is fine for xenon because it can have an expanded octet. And that's what the final molecule looks like once everybody's octet is full and we have gotten rid of all the valence electrons. Here's a list of all the atoms that have exceptions to the octet rule. Hydrogen, only having 1 principal energy level, only needs 2 to fill its octet. Beryllium only needs 4, boron needs 6, and then phosphorus is the first one to be able to expand its octet and hold 10 electrons, 2 more than the required 8 for most atoms. Sulfur can hold 12, halogens when they're the central atom can hold 12, and noble gases that do react can hold 12. As a side note, helium and neon are what we call inert elements, meaning they have never reacted with anything that we have ever seen.